So here we are with part C of the June 2018 Chemistry Regents Exam. I'm going to go over for you questions 66 through 85. These are short answer questions, really short answers for the questions in part C that you're going to go ahead and you would write in an answer booklet. So let's get to it. All right, so this first group of questions, 66 through 69, has to do with a little story here about Dmitry Mendeleev, and then you have this data table. And this data table, you are checking out some properties predicted by Mendeleev with regards to two elements that weren't found at the time. Okay, so 66, it's asking you to identify the phase of EA. So we go, of course, to EA. And first thing I want you to notice, and take your time when you do this, right? We're talking about something that has to do with aluminum, right? Otherwise, let's face it, that wouldn't be there. Then, of course, you have all of these properties here. And if we're looking for the phase at 310, we have to compare that to the melting point, and we're told it's a low melting point in 30 degrees Celsius. So first thing you want to do is convert your Celsius to Kelvin. On reference table T at the very bottom is the equation. So it's just going to be Kelvin is equal to 273 plus 30, or 303. And 303 is the melting point. Since we're at 310, that's above the melting point. So the phase here would be the liquid phase. All right, for 67, you're asked to write a chemical formula for the compound formed between EA and Cl. So we got to do a little detective work here. Let me erase this and let's check it out. So if you take a look at the oxide formula, it's given as EA2O3. And we know that oxygen would have a -2 for the either for the ion charge or for the oxidation number. And I needed 3 oxygens each gaining 2 or not sharing them equally. And -2 times 3 is a -6, but I have 2 AEs, so -6, I need a +6, and of course 6 divided by 2, EA is going to be +3. So now EA and Cl. So EA is +3, Cl typically wants to gain 1, so our chemical formula would be EaCl3. Now I want to also show you this, checking out the periodic table. Okay, so I'm here at the periodic table, and remember that the A stands for aluminum, so here's aluminum, and the rest of the elements here, right, including boron, aluminum, gallium, indium, they're all +3. So it stands to reason that we're dealing with EA +3 bonding with Cl. And I always tell my students, when you have the non-metal written second, of course, that and here, other than boron, the rest are metals. You're going to pick for the non-metal your top oxidation number. So we use oxidation numbers in my class when we're writing formulas. Cl's -1. I'm going to go ahead and crisscross the numbers. Your teacher might have done that with you also. And really what that's doing is balancing out the electrons lost and the electrons gained, and you end up with the same thing, EaCl3. Okay, in question 68, we're identifying the element that Mendeleev called this Eka silicon, or ES. So I have then silicon, obviously it's got to be related somehow with this. There's a couple of different ways that you can do this, but you are given the approximate molar mass, and you pretty much are going to know it's going to be in the same family or group as silicon. So you can go back to the periodic table and identify the element. Another way you could do it is to take a look at reference table S, because you have the actual density for the element and you have the melting point. The only thing with the melting point is you would add 273, and you can identify the element that way as well. Either way, what you're going to find out it is germanium or Ge for the answer for 68. So let's go back to the periodic table one more time and I'll show you. All right, back at the periodic table, here is Si, and look what's right below germanium, and we're dealing with that 72 grams per mole for the atomic mass. So Ge is your answer for that question. All right, for question 69, you're asked to show a numerical setup. That means you're plugging in the numbers into the equation, but you don't have to calculate out the answer for calculating percent error of Mendeleev's predicted density of ES. So we need the measured value and the actual value plug into the equation. The equation we're looking for, percent error, is here on reference table T. So we're going to go ahead and rewrite that back at the question, plug in the numbers, and we're done. Okay, so percent error is measured value, I'm just abbreviating, minus accepted value divided by accepted value times 100. Don't forget the 100. So when I'm looking at the densities here for ES up at the top, right, I'm just going to go ahead and plug in the numbers exactly as we have them. So it's 5.5 minus 5.3234 divided by 5.3234, and of course times 100. Don't forget the times 100, even though I can almost not fit it here on my screen. That's very important. There is your setup, and that was the answer they were looking for. Now, you can see here in this part of the exam, we had questions being thrown at us from all different places, and we have to be able to read the table. We have to interpret the data. You know, we're going back and forth between the periodic table, table S for physical properties, and reference table T for equations. In studying for the exam, it makes it difficult to know ahead of time what you're going to be dealing with here in table C. I just think go over your notes, review sheets that you were given by your teacher, and keep practicing questions. And with that, let's move on to question 70. Okay, the information that's given along with the equation is for questions 70 through 73. And we're told, of course, that this is a reversible process, and carbon monoxide gas and hydrogen gas are reacted using a catalyst, and the system is at equilibrium. So we want to keep that information in mind as we go through the questions. Sometimes you use the information and sometimes you don't. For 70, it's asking you to the class of organic the class of organic compounds to which the product of the forward reaction belongs. In other words, here is the only product, and I'm looking for what organic compound group does it belong to. Well, when you have more than carbons and hydrogens, you have what's known as a functional group on a molecule. So we're looking for the OH. Now, you might already know that it belongs to the alcohol group, but to make absolutely sure, or if you weren't sure, let me show you looking at the reference table. Reference table R, and we're looking for that OH, and sure enough, you can see here It's part of the alcohol class, and that's all you had to say. Alcohol or alcohols. So every single one of these class of compounds has something in addition to carbon and hydrogen on the molecule. Question 71, compare the rate of the forward reaction to the rate of the reverse in this equilibrium situation. Because it's equilibrium, the rates are equal. Write it down, equal rates, and move on to 72. For 72, we're explaining in terms of collision theory. This is with kinetics, why increasing the concentration of H2 will increase the concentration of the methanol. Well, if I increase the concentration of H2, I'm going to increase the number of effective collisions. And H2 is going to have with the CO, and therefore it's going to increase the concentration of CH3OH. You can just say it's going to increase the number of effective collisions, and you're done. 73. State the effect on the rates of both the forward and reverse reactions if no catalyst was used. Well, what do we know about a catalyst? Catalysts speed up reactions. So if no catalyst is used, then the reactions are going to proceed slower. So on the answer sheet, it asked the rate of the forward separate from the rate of the reverse, and you would put the exact same answer for both. They would both be moving slower, or just write slower, or you could say decrease as far as the rate. All right, 74 through 76 has to do with the information here and this huge molecule that you see in front of you. All right, so 74, we're writing the molecular formula for, I'm not really even sure how to pronounce this acid, but we'll just leave it as the acid. Molecular formulas are just the atom inventory. It's the element symbol and the number of times that element is in the formula. So what do we have here? We have carbon, we have hydrogen, and we have oxygen. So all you're doing is counting them up. So, you just want to make sure you're taking an atom inventory, and it doesn't matter whether you put carbon, hydrogen, or oxygen first. You just got to get the numbers. So you're literally just starting from one end, right? If this is carbon 1 and counting all the way across, and there are 18, but double check me. For hydrogen, that's a little bit more annoying, right? Because there's so many. So you want to pick one. I'm going to pick right here. I'm going to start with this as 1, and I'm going to go around this way. And when I go all the way around the molecule, there are 32. And then oxygen is easier because there's only 2. And there is my molecular formula. What you're seeing in front of you is known as a structural formula because it gives you the layout of the atoms bonding with one another in the structure. For 75, we're identifying the type of chemical bond between oxygen and hydrogen in this molecule. Well, what do I have? I have a nonmetal bonded to another nonmetal, and they are different nonmetals. So it is a covalent bond, but more specifically, it is a polar covalent bond. Now, I checked the answer key. New York State accepted polar covalent or covalent bond. So that would be up to you. They didn't ask you whether it was polar or non-polar, so covalent works for 75 in this case. Just make sure that you read the question as you're answering it. All right, and 76, let me erase this. On your diagram in your answer booklet, circle the organic acid functional group. So if you don't know the organic acid functional group, or you're not sure, you're going to go back to the reference table. And of course, I'm going to circle it here on the test, but you would circle it in the booklet. So when you have a functional group, I already mentioned, it goes beyond just carbon and hydrogen. So we're focusing our attention on the oxygen. So here is the functional group. Sometimes you'll see it written as COOH. It's shortened a little bit, but let me show you it on the reference table, but that was the answer. Okay, we're back here at reference table R, and here is the acid, and there it is. So COOH. Okay, we're getting closer to the end here. Questions 77 through 79. We have a picture of a cell. Now you're told right away here it is a voltaic cell. So it's going to produce electrical energy. And actually you see it here and they tell you here. And they give you an unbalanced redox reaction. They give you some information here and they give you a diagram. All right, so let's take a look at the questions. Let me erase that. All right, so the first one here, 77, we're going to balance the equation in the answer booklet for the reaction of the fuel cell using the smallest whole number coefficients. Okay, so here we are. I went ahead and figured for this one we better have the answer booklet. And 77, you see the equation and you want to balance it. That means that the elements and the number of atoms on both sides of the equation have to equal out or balance out. So I just tell my students just move from left to right. In other words, I have 2 hydrogens here, I have 2 hydrogens here. Right now it's balanced. I go to oxygen, I have 2 here, but I only have 1 in H2O. So the only thing I can do is bring up the side that has less. I'm going to put a 2 in front. That's known as a coefficient. That means it's 2 waters. That means 4 hydrogens, 2 oxygens. So now my oxygens are balanced, and I need to go back and put a 2 in front here. Now it's balanced. Now you could put the number 1 here once it's balanced, but you don't have to. It's understood that it is 1 when there's nothing in front of either an element formula or a compound formula in an equation. All right, in 78, we're determining the change in oxidation number for oxygen in this cell. Well, I'm going to go back up here, right? Here is the equation. So it's going to be easier to do it with the equation. And we don't have to use the balanced equation from the answer booklet, I guess, but we could. So let's just focus in our attention on oxygen. Oxygen is alone, it's not bonded with another element, so the oxidation number is 0. And with water, oxygen has the oxidation number of -2. So it's going from 0 to -2. Okay, finally in 79, state the number of moles of electrons that are gained when 5 moles are lost. They have to be equal. Moles lost are equal to moles gained, or moles gained are equal to moles lost. In other words, 5 moles. All right, let's keep going. We got 5 more to go. First question here for 80. We're told about 4 different solutions for HCl, and here they are. And now in 80, state the number of significant figures used to express the concentration of solution Z. Well, if you take a look at solution Z, my concentration is a number less than 1. So we are going to move from left to right and find the first non-zero, which is the number 1, and anything to the right of that number, which is just that 1 0. That makes the number of sig figs 2. Find the video to refresh your memory on significant figures if you don't remember how to deal with them. Everybody has maybe a slightly different way to approach it, but it's all the same. It's just that zeros sometimes are placeholders, and in this case, these 3 here were, and then sometimes zeros are part of the measurement, which is the 0 to the right of 1 in this case. All right, let's move on to 81. For 81, we're determining the concentration of an HCl solution that has pH of 4. So there is a trend going on here that they give you in this table, right? We're going from 0 to 1 to 2 to 3, and now we're going to 4. So you could just follow the pattern and say, hey, wait a minute, look what's happening each time. The decimal point is going to the left. So for number 4, it's going to be 0.00010. And that's exactly what the answer is. Now, I also teach my students that there is a connection between pH and the exponent for the hydrogen ion concentration, 10 to the minus. In other words, if I have a pH of 4, my hydrogen ion concentration is 1 times 10 to the minus 4. This value and this are exactly the same. Either answer is correct. All right, for 82, we're determining the volume of 0.25 molar sodium hydroxide that's going to exactly neutralize 75 mils of solution X. So what do we got in solution X? We got 0.1 HCl. Oh, we're talking about neutralization. We have a mathematical equation for that. You got to go to reference table T. Okay, so the titration equation is right here, and that titration equation has to do with an acid neutralizing a base, just like a base neutralizes an acid. So the question is asking for the volume, so we're actually going to calculate the answer here. So let's go back and do that. I need to write down the equation so I can show you how I'm plugging it in. Molarity of the acid, volume of the acid, molarity of the base, volume of the base. I always tell my students to put the formula for the acid and the formula for the base on either side in case they want to throw you, they meaning New York State, a curveball. They could give you a different acid like a diprotic acid or a dihydroxy base. But in this case, it's a 1-to-1 ratio, so it's all good. All right, so determine the volume of 0.25 molar NaOH. So let's change the color here. Let's go with a pretty purple. So it's 0.25, right, is the concentration of my base. I'm looking for the volume of my base. On the other side, remember, it's solution X. Solution X is 0.1, so it's 0.1 times 75. All right, and we need the volume here. So 0.1 times 75, which is 7.5, then divided by 0.25 to get the answer, which was 30 milliliters. Fantastic. We have, let's see, we're at 82. We got 3 more to go. Okay, for this last set of questions, we're given some information here to read about CO2 and seawater, and then we have a graph that has to do with the solubility of calcium carbonate and molarity, and you can't see it right now, but I'll scroll in a minute, the pH of seawater. So look what's happening here. As the solubility is getting less of the calcium carbonate, the pH is obviously going up. So let's check this out. Okay. Question 83. State the trend in solubility of the calcium carbonate as the seawater becomes more acidic. So be careful here. More acidic means my pH is going this way, right? The lower the pH value, the more hydrogen ions or the more acidic the solution. So as we're moving here and the pH is dropping, the solubility is increasing. And that's what you had to say. All right, so for 84, we're asked to state the color of brome cresol green in a sample of seawater in which the calcium carbonate solubility is 10 to the minus 2. So we need the pH, and then we need to go to the reference tables to find the color. 10 to the minus 2 on that graph. I'm going to go here, and I'm going to go down. So it's above 6. I don't think it's 7, so it's between 6 and 7, the pH. So let's go check out the reference tables. We were asked to figure out the color using brome cresol green, and we said that the pH of the seawater was between 6 and 7. Now, just very quickly, the way that you read the color for the indicator with, let's do brom cresol green. Less than 3.8 is yellow. Greater than 5.4 is blue. And sure enough, 6 to 7 is above 5.4, so our answer is blue. If we were asked anything in between these two numbers, yellow and blue make green. So that's how you read for each of these indicators on reference table M. But the answer to the question was blue. Final question, 85. Sample of seawater has a pH of 8. Determine the new pH of the sample if the hydrogen ion concentration is increased by a factor of 100. So you can think of pH as a number line. And you want to watch a video on this. I think it would be helpful. I know that I have one on this channel that is good for a review, but if you think of it as a number line, I think you're going to be fine. If we increase the hydrogen ion concentration, that means more acidic. More acidic means that the pH is going to get lower. So every change in pH number, the hydrogen ion concentration changes by a factor of 10. Well, 100 is 10 times 10, and it's increasing. So as the concentration's increasing, the pH is getting lower. So it's going from 8 to 7, and then 7 to 6. And that is my answer. So anytime you're dealing with changes in pH, a number line will work just fine. This ends Part C of the June 2018 Regents exam. If you went through the whole thing, that is awesome. You should be proud of yourself. Keep working on questions and give me a thumbs up if you like the video. And I hope that you keep working hard, and good luck on that Regents exam.